Welcome to today's episode. We're diving into a groundbreaking topic that merges AI innovation with business impact: bootstrapping long-context language models. Joining us are top experts in AI, machine learning, and business strategy to unpack what this means for enterprises, tech leadership, and innovation.
Thanks for having us. We're standing at the edge of an AI revolution, and context length is one of the key battlegrounds. Extending an AI model's ability to process 1 million tokens changes everything, from enterprise analytics to research augmentation.
Absolutely. Imagine a legal firm reviewing thousands of case laws at once, summarizing arguments, and predicting case outcomes. With this technique, models can retain and reason over much longer documents in one shot, eliminating costly multi-step retrieval processes.
Not just legal. Think of global corporations managing compliance, companies like JP Morgan, or multinationals that have regulations from multiple jurisdictions. They could use these models to digest and align their policies without manual cross-referencing, which is both expensive and error-prone.
That's a great setup. But let's break down how this bootstrapping technique actually works. Can you walk us through it?
Sure. The core idea is to use short context models to generate long context training data. Instead of manually sourcing large datasets, because, let's be honest, finding documents that naturally extend to 1 million tokens is rare, we use an agent workflow.
And this agent workflow mimics human reading behavior. First, an AI generates diverse, instruction-based queries. Then, it retrieves related documents using a text retriever, applies query-focused summarization to filter out irrelevant content, and stitches together a response that forms a long-context training sample. Exactly. And what's brilliant here is that every step only involves short input sequences. That means we're taking an AI that originally understands 4K tokens and getting it to think in million-token scales just by orchestrating its workflow.
It's like training a chef to cook for a banquet by having them master individual dishes first, then assembling a full-course meal. We're not demanding the model suddenly know how to process massive contexts. We're progressively training it.
Love that analogy. But let's get into the technical nitty-gritty. You mentioned retrieval augmented generation earlier. How does this play a role here?
RAG is the secret sauce. Instead of the model hallucinating information, we retrieve actual documents from a corpus. This ensures factual accuracy. A Fortune 500 company could use this to generate executive briefings from real-time market reports, rather than relying on outdated knowledge embedded in the model.
And for those worried about inference speed, yes, processing 1 million tokens is computationally heavy. But techniques like ring attention distribute computations across GPUs, making long context processing feasible even on current hardware.
Right? And businesses need to think about this pragmatically. If you're a CFO or CIO at a multinational, what you care about is cost-benefit. Do you spend millions hiring analysts, or do you deploy a model that can read, summarize, and synthesize information from 1 million token corpus in minutes?
That brings us to a key business question. What's the ROI? How do you quantify the impact of this for enterprises?
Well, let's take pharma. A drug discovery pipeline generates enormous volumes of research. Right now, it takes years to validate findings because researchers manually cross-reference thousands of papers. A long-context AI could synthesize this knowledge near instantly, cutting discovery times drastically.
Another example, customer service. A telecom giant handling millions of support tickets could use a long-context LLM to analyze historical queries, pinpoint patterns, and proactively resolve issues, saving millions in call center costs.
And let's not forget financial risk analysis. Think about hedge funds or insurance firms, evaluating macroeconomic trends across decades of reports. These models could do that in real time, something that was previously infeasible.
So we're talking about direct cost reductions, efficiency gains, and entirely new business capabilities. But are there risks here?
Always. There's a lost-in-the-middle problem where longer contexts dilute relevance. Fine-tuning is key. Also, inference costs are non-trivial, so companies need to balance model size and deployment strategy.
And security. A model capable of processing vast amounts of proprietary data must be air-gapped or run in highly secure environments. No company wants its sensitive documents accidentally exposed.
Fascinating. So, as a final thought, if you're a business leader listening to this, what's your immediate takeaway?
If you're not already exploring long context AI, you're behind. This will redefine knowledge work, and the winners will be those who adopt early.
Start with a pilot, automate document-heavy workflows, and measure the efficiency gains. You'll be surprised how quickly the value manifests.
Partner with your AI teams. This isn't just IT, it's a business transformation.
Long context AI is more than scaling token limits. It's about designing workflows that integrate retrieval, summarization, and reasoning to maximize efficiency.
And don't just scale blindly. Focus on inference optimizations, efficient memory usage, and real-world task alignment to ensure business impact.
Brilliant insights. Thank you all for an incredible discussion. We're going to take a short break on today's episode. Until next time, keep innovating. Welcome back to part 2 of our deep dive into long context language models. This segment is all about the technical side, geared towards AI engineers, AI architects, and CTOs looking to implement and optimize these models for real-world applications.
Let's start with the foundational mechanics. The core of this approach relies on short context LLMs generating synthetic long context instruction data. Instead of manually curating vast datasets, we use an agent workflow to break down the data synthesis process into discrete, manageable steps.
Right. And a key enabler here is rope scaling. Normally, rope embeddings encode positional information up to a fixed length. To extend context windows beyond their original limits, we modify the base frequency of rope, ensuring embeddings remain meaningful at longer sequences.
But just extending rope isn't enough. Without proper fine-tuning, models trained with extended embeddings suffer from severe degradation in retrieval and coherence. That's why we progressively train across increasing context lengths, starting at 128K, then 256K, 512K, and finally 1M tokens.
So you're saying progressive training is critical. How does it work in practice?
Think of it as staged curriculum learning. At each stage, we quadruple the rope frequency and train on longer contexts while retaining prior learned knowledge. This ensures models don't just memorize long inputs, but actually learn to utilize them effectively.
And inference is another beast entirely. A naive approach would require quadratic memory for self-attention, which is impractical. Instead, we leverage flash attention and ring attention, two optimizations that enable efficient scaling by distributing key-value caches across GPUs and reducing redundant memory usage. Another challenge is the lost-in-the-middle problem. As context grows, models struggle to retain focus across long sequences. One way to mitigate this is through retrieval-augmented generation, RAG, where documents are selectively reintroduced during inference rather than relying purely on extended token windows.
Absolutely. And for real-world deployment, you need more than just theoretical optimization. Techniques like speculative decoding and mixture of experts, models, allow us to scale inference while maintaining quality.
A great example is how financial institutions use these models for fraud detection. They analyze millions of transactions spanning years. Without optimizations like hierarchical memory management and selective reprocessing, running these models at production scale would be prohibitive.
Another key takeaway is dataset construction. High-quality, diverse data is paramount. We bootstrap instruction tuning using a recursive summarization approach, breaking large documents into smaller query-driven chunks, summarizing them iteratively, and reconstructing long context outputs.
And beyond that, we apply instruction back translation. This means taking a long document, generating synthetic queries, and then training the model to reconstruct the document from these queries. It's a reverse engineering approach that helps ensure the model generalizes well.
Incredible insights. Before we wrap up, any last words for AI engineers and CTOs looking to integrate these techniques?
Start small. Experiment with retrieval-enhanced transformers before scaling to full long-context architectures.
Focus on memory-efficient training. The biggest bottleneck isn't compute, it's GPU memory bandwidth.
Fine-tuning on high-quality, well-structured datasets is more important than sheer dataset size.
If you're doing real-world deployment, prioritize inference optimizations like ring attention and dynamic retrieval over raw model scaling.
And lastly, explore hybrid approaches. Combining long context models with traditional retrieval and summarization pipelines often yields the best results.
Fantastic discussion. That concludes our deep dive into the technical underpinnings of long-context LLMs. Thanks for joining us, and stay tuned for more cutting-edge AI insights.